So I'll start off by thanking Stephen for the invitation and WCI for hosting the seminar series. And the presentation that I'm going to give you today is a grab bag of a few of those different topics. We'll talk about kind of the big concepts that we've been working on at Argonne National Lab. We'll talk about some specific software and pain points, and then we'll wrap up with a discussion of how we can leverage the fact that we've got such a vibrant community around workflows to really accelerate the development of AI applications inside of workflows. So I'll start off by touching a little bit from my background as a physical scientist. And one of the common tools that we use in physical sciences, and certainly this is preaching to the choir, are computational campaigns, where one enumerates a large set of potential calculations to run and then employs a workflow engine to execute as many of them or as possible. And this is something that's certainly non-trivial, and it's certainly a useful tool, but it isn't a great use of high performance computing resources. And one of the things that I've been working on since I joined the now belated exascale computing project is how we can take these computational campaigns and make them really effective users of the largest computing resources. And really, the problem is with these sort of computational workflows is that our computers are too fast. The conventional route of being able to run a series of calculations, think about them, and then adapt to what the outcome was in order to identify the next set of calculations is something that if we hadn't scaled out of that ability within the past 15 years, we're almost certainly out of it now with the advances in high performance computing. What we need instead of a human taking days or hours to decide what to do next, we need some way of allowing the supercomputer to process the outcomes of each of those parts of the campaign and use it to narrow down what calculations we actually need to be able to answer a question. So with that sort of architecture in mind, I've got two components of my workflow now. I've got something that decides what to do and something that does it. There's a large degree of room for freedom in how to implement these. Looks like my bottom line already popped up on this slide, but we'll ignore that for a moment. Really, the root problem here is because I have two types of calculations, something that decides, something that does. There are many ways I can lay them out. I could do a batch process, which is great because each time I make a decision, I have all the information available, but I could have tail down losses. On the other hand, I could have a task queue that is periodically updated at the expense of leveraging the most information to pick the next task. So really what the point of this talk is going to be is that there are not just three ways of being able to integrate AI and that simulation engine together, but very many of them. So we need some kind of flexible tools to be able to build these campaigns. So what I'm going to do first is go through a little bit broader of a scope of what these AI for HPC applications look like, illustrate the way that myself and my team at Argonne have been developing tools, which is one way of looking at the problem, and then make a pitch for what are the kinds of activities we could do as a community to be able to build a collective ecosystem, allowing many of these kinds of tools to be built. So with that said, I want to skim a little bit over the top of the kinds of application patterns that exist for coupling AI to conventional science workflows. And I'm only going to branch over the top of this because it would probably be great to drag Shantanu Jha or one of his team members to give a more detailed overview. But the idea is that there are many different application patterns for being able to integrate AI into an application. I tend to look through the steering types of applications, this AI improving HPC loop, where I have simulations occurring, some sort of analysis, deciding what the next set of calculations are, as we've discussed earlier. But there are many different sorts of patterns depending on where the application itself uses AI. Now, backing out from this way of describing the pattern of where does the AI lie, the way that I'm more comfortable with talking about it is what kind of AI in the loop we can do for building these applications. And I'll talk through a few of these over the course of our talk today. If I'm looking at a high throughput design problem, which is an optimization at the core, there are a branch of classes of applications called active learning, where I take the outcome of one simulation, use that to update my expectations about what the outcome of others will be, and then impart a policy that picks. So I have this loop model. Generative AI, which is one of the other certainly popular types of AI today for good reason, has another sort of application pattern. I'm generating text that I then score. I move that back to a training set that is used to refine my application patterns. And these are but a few of the kinds of AI applications and surrogate or uses inside of workflows that may be possible. So with this sort of broad overview in mind, let's dig in a little bit further and talk about like how one could express and implement these types of applications. Which that brings me to the work that we've been doing more specifically at Argonne. And as I discussed earlier, back in the beginning of the talk, and have highlighted slightly through this brief overview of the types of application patterns that exist, we can hopefully see the conclusion that when you're expressing a algorithm on how AI is being used inside of an application, be it a when new calculation completes, start another one, and then retrain a model if new data has been acquired. A lot of these kinds of application patterns are described in these sort of if-then or simple agent descriptions. So what we've done as a team at Argonne is built a way of expressing these kinds of agent-based policies in a familiar programming language, i.e. Python, such that we can use them to specify a large-scale application. So we're not going to touch in the deep details on this, but I do want to show you a little bit of code to help kind of solidify the picture of what these kind of AI applications can look like. Here you see a simple application with two different policies. The first is a simple one. It consumes a completed task and checks if the outcome of that task was better than anything else before. I update the state of my system to tell me where the best outcome was, which feeds forward into the second policy that continually generates new tasks by taking the best guess that we've identified so far in the other policy and using that to propagate through some kind of AI algorithm. So the idea is that we can decompose these workflows into both a set of simple tasks. Here I've got a simulation task and I have a task generator method that are both executed on some remote resource, and they're coupled together via a series of policies. You can take that idea and expand it out a little bit further. Here is the kind of application that we built in 2019 to be able to implement the active learning type policy I described earlier for executing a high throughput design. You'll note here it's decomposed into 6 policies. Let's see, I'll make sure you can see my cursor now. Defined here that each implements something very simple, like this machine learning recorder receives a AI task that inferred the properties of molecules and uses that to update a queue of potential molecules to run that are then executed by the QC scorer agent that launches a new task every time resources become available. So by clinking together each of these small agents, coupled with some persistent services like a database, we can build an application with some interesting emergent behavior. So this is what running that application looks like. Here I'm showing you the outcome of what is running on 120 or 1,024 nodes of the Theta supercomputer over the course of 6 hours. Color indicates what type of task it was doing. Yellow is inference. Dark shades indicates that node was actually producing useful results or results that we use at the end of the simulation. And you'll note here it starts off with a inference phase, where I dedicated all nodes to the inference tasks. I then switched over to using everything for simulation and periodically updated my machine learning models before rerunning the inference tasks, which fed forward into what simulations are run. And this complicated procedure ended up netting us some benefits. So here I'm showing the number of good molecules. These are molecules for batteries. So we're trying to find ones that store a lot of energy when you ionize them. And you'll note in yellow, my policy that used this steering strategy definitely outperformed a AI with less search randomly through the space, but it also performed a policy where I did not have that loop. I only used some machine learning models at the beginning to pick where I was going. I did not update them. And by 4 hours, the decisions that I made at the beginning were outdated based on the results that were coming out of the supercomputer. And I lost about 10% or 20% effect by not integrating AI into that workflow. So what it's showing us is that we can get out of the same allocation of compute resources, more scientific outcomes if we engage those AI algorithms effectively as part of the workflow. And this is something, of course, that besides implementing the policy, has some other challenges that we've been working to address over the years. Getting Python to start on a compute node, certainly a problem that I'm not the only one here who's encountered, is something that costs us a lot of our compute time. The two areas loading TensorFlow into memory was particularly challenging, and you could see that at hours 0 and 1, especially. Another question is, even if we did manage to deploy on 400 nodes and get a Python interpreter running, were we actually using them effectively? That in itself was difficult. We had to implement a secondary data fabric in order to send the machine learning model and the inputs that it was running inference on through a separate channel outside of the workflow engine, such that we wouldn't see data bottlenecks. Here, it took 10 seconds to send a task from the workflow engine to the compute node, which disturbed our ability to run over 500 nodes, only an eighth of the supercomputer. Where once we added this fabric in, we were able to not only scale better, but achieve that. This data fabric is something that we implemented as a secondary channel. You mark what the data for the tasks are. They are stored as data in a Redis subsystem that are then passed by reference and accessed on the compute nodes. And this is something that, which we'll highlight later, was not part of Colmena. This is a secondary package that can be used by other compute systems. Since then, I believe we've used it with Dask, among others. So moving forward, there are some other performance problems that we have worked to address over the years. Training took 30 minutes, which was a notable chunk of our compute time. We were able to accelerate this by offloading our calculations from the CPU nodes of the Theta supercomputer onto a more AI-appropriate hardware, a small GPU box. And this is something that we implemented by using that data fabric and the Globus Compute workflow tool. And we're able to achieve a very high utilization of our original resources and very small latencies at the core steps of our workflow, like passing our completed machine learning models back to the compute nodes for inference, in such a way that we're able to achieve the same scientific outcomes using this cloud-hosted system without having to set up any SSH connections between our two compute nodes. We're able to get that same scientific compute or scientific outcome without any of that networking hassle. Additionally, some of the other things that we've been taking a look at as a team are being able to address the kind of tail end of a computing task. Our workflow contained many long tasks. Some didn't finish by the end of the workflow. So what we've been doing now is breaking each of our tasks into smaller chunks, which do two things. One, ensure that data from each task are complete and stored by the time our CPU allocation runs out, but also being able to use the fact that we're having more chunks of work that are being done to actually use AI more effectively in the loop. We could decide, say, between the first series of the calculation that it's not likely to achieve a good outcome, and use that to reduce the amount of high fidelity calculations that we employ. So by breaking this up into chunks, we can get a better scientific outcome with the same resources, yet this again requires more cleverness on the implementing the policy side, yet again really motivating our need to write these kind of workflows. So this is something that we've continued to work on. I'm only going to briefly touch on these today so that we can save some time for questions. Are the way we've been integrating generative AI is to create a system that tests the predictions made by that generative AI, say one that invents a new material for CO2 storage. We've implemented a series of workflow tools that will go back and evaluate whether that was actually a good material in the first place. And if so, you use it to refine the generative AI so that it better mimics good materials rather than bad ones. And this is something that we can do for training generative AI in one way. We've had another strategy that uses a similar workflow but engages reinforcement learning as a mechanism for tuning that generative AI. And all of these, to emphasize, rely on the ability of writing these policies that directly interleave the AI with the simulation as part of the same application. And that isn't the only, and Colmena is one way to do that. That's the way we've been approaching it as one team at Argonne, but it's far from the only way of looking at the problem. So really, Colmena was designed with writing these sophisticated policies, but there's a lot of reasons to avoid it. The fact that we have a centralized policy engine means that we are limited in the rate at which we can make decisions, typically about 1,000 a second is the most one could expect from a workflow. So if you have a workflow that's scaling out to tens of thousands of nodes, and those tasks are very short, you'll need to do some additional mitigations to make it scale with Colmena. That may not be the case for other tools. Additionally, it's a very bare bones package. If you want to integrate with an optimization library, for example, there are better choices out there. So I brought up the picture here, which you've had a chance to look at now. Colmena is just one of a large set and growing set of tools for implementing these sort of AI in the loop. If you want to be able to directly interface with a advanced math library, LibEnsemble, which Steven's one of the developers of, is a great choice. It also has a very simplified model, which means you can start up with it faster than with Colmena. And there's also Ray, which allows implementing distributed policies in a way that's difficult with Colmena, yet necessary or at least extremely effective for implementing distributed policies like deep Q networks for training reinforcement learning. And as I mentioned, there's a very broad tool and you can measure them in different ways. And this is something we've been thinking about for a while. And given the fact that there are so many ways of approaching these problems, and they're all going to experience very similar issues, one thing that I've been advocating for, and I imagine I'll find more fellow travelers here in the Workflow Communities Initiative, are assembling sets of external tools that allow for addressing many of the common challenges for these AI in the loop applications. Two of the ones that we've tackled and you've heard touched on a little bit today are being able to pin GPUs. That's something we implemented or pin tasks to GPUs. That's something we implemented in Parcel. The data fabric is a whole separate application from Colmena, proxy store. Lots of great other reasons to use that tool, and it's totally accessible outside of our ecosystem. And these are only scratching the surface of the kinds of problems where there are emerging solutions that hopefully we can support as a community or at least make aware of so they can be used more broadly. So with that said, hopefully this leaves us some time for questions. If not, I'm hopeful my email address was associated with the presentation. If not, you can find me via Argonne. I've talked to you today about both the narrow lens of how we're approaching this broad spectrum of problems at Argonne and hopefully scratch the surface on some of the challenges and potential solutions we have for addressing the challenges in integrating AI into larger workflow applications. So at this point, I'll be happy to answer any questions that you guys have. And thanks again for the invitation.